So here we have a insightful and a very challenging problem of electrostatics from Exemplar Physics Ncert of class 12. But this problem is of the level of JEE Advanced, and as you will see, it requires a lot of physical insight, and there are a lot of aspects which are covered in this problem, and it is what makes this problem a multi-concept problem. There are a lot of concepts, and I think it is a very good problem for JEE Advanced. So there are basically a lot of ways to solve this one, and if you follow the book, I mean that NCRT Exemplar Physics, Problems in Physics by NCRT, basically that solution which you will get at the end, you might not be able to completely understand that solution. You might not grasp all the aspects which they want you to understand in the solution, and it is in that sense that makes this problem really very difficult and of genuine quality in testing your analytical ability to apply simple concepts of physics to solve a new physical situation. So in this video we will not only do the book solution, we will not only go through the solution which is actually given in the book, which is also a very standard way of doing this one. The book problem has its own standard solution printed, and if you go through it, there is a chance that at a first glance you might not get all the points from that solution, so making the problem equally difficult to understand even after going through the solution. But there is another way of doing this problem, and I have perhaps discovered that way of doing this problem, which is really astonishing, as I will show you in the end that we have used two very different methods to solve this problem. The two methods I will show you in this video are going to be very different in solving especially the part C of problem 1.28 of NCERT Exemplar Physics class 12. So let's begin this problem session, and I think it is going to be very insightful and fun, in a sense that it will give you a lot of challenge in understanding the problem in the first place and proceeding. So let us begin. First I will do the solution which is already present in the book, and then we will dive into the approach I have discovered. And I think at the end it is not only important to solve this one, but I will show you how these two different approaches have some analogous character in them, which is what makes this problem again a bit interesting and challenging at the same time. So without further ado, let us begin reading the problem. Two fixed identical conducting plates alpha and beta, each of surface area S, are charged to minus capital Q and small q respectively, where capital Q is greater in magnitude than small q, and all of these charges are non-negative. That is, they are positive charges. And this little bit of information that small q is a non-zero charge is of great physical importance in this problem. I'll show you that, how this is important and why they have mentioned it in the first place. So third identical plate gamma, free to move, is located on the other side of the plate with charge q at a distance d. The third plate is released and collides with the plate beta. Assume that the collision is elastic and the time of collision is sufficient to redistribute the charge amongst beta and gamma. First part, find the electric field acting on the plate gamma before collision. Okay, so let us first remove this thing. Yeah, so we begin the first part of the problem, which is to basically find the electric field. Let us say that this is plate alpha, this is plate beta, and this is plate gamma. So as you see, let us name this as alpha, this is fixed, This is plate beta, which is fixed, and this is plate gamma, which can move freely. Plate alpha has some charge minus capital Q, plate beta has some charge small q, and plate gamma has some charge, as if you carefully see the diagram, it is positive capital Q, such that it is given that the magnitude of capital Q is greater than small q, which is greater than 0. This condition is very important. This has great physical importance in the problem. I'll show you why. Without this piece of information, a question could be raised by the guy who is kind of solving this problem, and I'll show you. This type of small physical aspects are not at all covered in detail in textbooks of such magnitude, and this is why this becomes a nice problem, as I said. So let us delve deeper into the first part. We have to find the electric field due to conducting plates beta and alpha on this plate gamma, right, before collision. So before collision, the plate gamma is located at some distance d from plate beta, right? Now, if you can recall, what is the electric field due to a conducting plate with some charge? Let's say that this is a conducting plate with some charge q, or we can say it has some cross section area A, or we can say that it has some surface charge density sigma. What is the electric field at this point due to this conducting metal plate? Note that I am drawing the diagrams in a two-dimensional plane, so it might not be a plane. I mean, a plane looks like this. This is what a plate looks like. Now the electric field at this point, let us say this is some point x and it is at some distance r from this. So if you remember from your basics of electrostatics, we assume a Gaussian surface which is cylindrical in shape, and we can compute the electric field at this point x due to this charged sheet or charged conducting plate. What is it? We can directly write it. I'm not delving into that part of deriving from that as an application of Gauss law. So we get the expression as the surface charge density upon 2 epsilon naught, or you can say that the surface charge density is basically total charge upon the cross sectional area. So you can express the electric field as equal to the total charge upon twice area times the epsilon naught constant. Now what is this epsilon naught? It is the electric permittivity of the medium, a very characteristic property, intrinsic property of the medium we are talking about, the electric medium. And if you notice, this electric field has got nothing to do with the distance at which the point is located from this plate, right? And this is the basic expression which we are going to use and compute our first part. So let us go back to our problem, which says that there are 3 metal plates. So this is plate alpha, this is plate beta, and this is plate beta. They are identical, and this is plate gamma, which can move. So this is alpha with some charge minus q, this is beta with some charge q, and this is gamma with some charge, oh, that doesn't look like a gamma, with some charge capital Q. So what is the electric field due to beta on gamma? This is how I write the expression of electric field. So let us say that so it is given in the problem that the cross sectional area of plates alpha beta is S, right? It is given. So all we can write is that it is Q upon 2 times S epsilon naught, right? And what is the electric field due to plate alpha on plate gamma? It is, we are writing these expressions before collision, right? The plate has not collided. We have not released plate gamma. If we release it, it will just kind of collide with plate beta and then perhaps rebound back, and there's an interesting phenomena which will follow, which makes this problem justified to be of the level of J advanced. So the electric field due to plate alpha on plate gamma is this one, and I wrote this minus sign. This is because it is given in the problem. This is the positive x direction, this is the positive y direction. So basically the electric field due to this plate alpha is in this direction. Electric field due to plate beta on plate gamma is in this direction. as you would expect, and hence we can define this thing as the x cap direction to define our electric field vectors, right? So what is the net electric field? Well, all we can do here is that we have to add these two expressions and we get the net electric field. What I wanted to say here is that this is having some charge q, so the net electric field E net is E alpha gamma plus E beta gamma. So how much is the E net? We can write it like this: q minus small q by 2s epsilon naught times, we are writing a vector equation, so we must mention the unit vector in, so which will specify the direction of our electric field vector. Some of you may be wondering that it is kind of quite non-intuitive that this thing is negative, right? Then how come we write capital Q minus small q? It is because we are writing the magnitude part. See, this part is written in terms of magnitude, and in terms of magnitude it is given that capital Q is greater than small q, right? But the direction of this net field will be somewhat in this direction, not on beta, it will be on alpha, on gamma, but this is how it will look like. And so we can write the net electric field like this. We can write it like this. This is just a vector equation, and whatever you mention to be the direction of the unit vector, you can accordingly write the total electric field on plate gamma before collision. So this is our final expression. Now we move on to the second part of this problem. What is the second part? Well, it says something like this: we have to find the charges on plate gamma and beta after they collide. See, before they collide, gamma was at a distance d from beta, right? Now why will it collide in the first place? Because when you release plate gamma, it is given that it is free to move, so it will experience this net electric field I wrote a while ago, and hence it will experience some force due to this charge q in red, and hence it will accelerate towards plate beta and collide with it. And beta being stationary, gamma has a high probability to get just kind of retrace its path and rebound properly, and might again return to that distance d from beta, right? So instead of confusing you, let us just do the second part, that is, we have to find the new charges after collision takes place, and as given, the time of collision is sufficient for charges to redistribute. Now why will charges redistribute in the first place? It is because when the plates gamma and beta are in contact during a very small instantaneous moment of time, then they are at the same potential. This is a very important concept to understand here. When two metal plates are in physical contact with each other, they are necessarily at the same potential. If there is no electric device between them, you're just simply connecting two conducting materials together. They're in physical contact, you can say they are in electrical contact, and hence they are at the same potential, same electric potential. And from this idea we can get what is exactly the charges on them after they collide, the new charges. So let us assume the charges after plate beta collides with gamma. The charge on beta becomes q1, some q1, and the charge on gamma becomes some q2. We do not know what q1 and q2 are, and that is what we need to find out. But what does law of conservation of charge say? It says that the total charge of an isolated electric system is conserved, which means the initial charges were capital Q plus small q, so that must equal this one. This condition needs to be satisfied at all costs. Remember this condition, and also remember at this point I bring in that little piece of information mentioned in the problem in the very beginning of it, that small q is a non-zero charge. This has a great physical significance. See, If it was not mentioned that small q was a non-zero charge, then you could simply assume that it might be zero, and this expression might have got modified in the process of solution and a question would have been raised, but it is now properly neglected. See, what I want to say is that basically a non-zero charge has its existence at all costs, which means this expression will stay just as it is. This conservation charge law, this thing will remain like it is. You cannot modify this one at any cost. This thing is non-zero, right? Remember, this is our first equation in finding q1 and q2. Now we move on to the second part. How do we go about? Remember, I said that the two plates, when they are colliding, they will have the same electric potential. They will not have any difference in potential, right? And that does mean something like this. If I get the plate gamma a bit closer to the plate beta, basically this is plate alpha, which is stationary, plate beta is stationary, and this is plate gamma. Now let us consider a point here. Let us consider that point, yellow dot. Let us name that as point O. Don't you think that when these two plates collide, right, that point is in that region where the two plates are in physical contact with each other during that small instantaneous time of collision, and hence they are at the same potential, the same electric potential. And what does this piece of information give us? Does it give us some helpful expressions? Yes, it does. What are we getting? See, we know that the electric field at any point in space is expressed like a negative of the potential gradient. This is how we can define electric field in terms of potential gradient, right? A negative potential gradient. When I say the point O has a constant value of electric potential, I mean the plate beta and gamma are at the same electric potential. It means there is no change in potential in the point O or near the region where point O lies, which means this dV is 0, which means electric field is 0. Or we can say that the electric field at point O is 0. This is something which was not clearly mentioned properly in that solution. So we can say that if this is point O, then we can say that the electric field at point O is 0. This electric field is due to all factors external to this point, which means electric field at point O will be due to plate beta, will be due to plate gamma, and will be due to plate alpha. Now for computing that type of an electric field, we will consider a moment just before collision, a fraction of a second just before collision. You know how close the plates get to just before collision. We will consider that moment. Perhaps that will help us to compute the electric field just before collision, right? Just they have collided, or you can say it's that instantaneous moment that they have collided, not just before collision. To be more precise, they have collided, and we consider that instant when they have just come into contact, and we just take that moment and we do our calculations. So let's start our next computation. So here we have our next computation to find the electric field at point O due to those plates when they are just in contact with each other for just a little bit of infinitesimal amount of time, a very tiny time. I'm drawing it like this to make point O clearly visible. This is alpha, this is beta, this is gamma, and after, let us say, when they are in contact, charges have redistributed, and momentarily beta gets this charge q1, alpha has that same charge capital minus q, and gamma has the charge q2. So what is the electric field at O due to the plate gamma? So we write that as E gamma dash after collision. These things are just after, post impact, right? So what are these expressions we are getting? It is Q2 by, this is the electric field at point O due to plate gamma, 2s epsilon naught. Electric field at point O due to plate beta. The dash represents post impact parameters. So that is Q1 by 2s epsilon naught. And the electric field at point O post impact due to plate alpha is something like this, right? Now what I want to ask is that we have three expressions for three different electric fields at point O, so they must all add up to be 0, right? Because the plates beta and gamma are in at the same electric potential, which means there is no change in potential, which means the electric field at that point will be 0. There will be no gradient in potential, so E is 0 because dV is 0. So E means total electric field at the point O due to all these external factors like E dash beta, E dash alpha, E dash gamma. We just add them. Now one thing, this is the point where that fact y which was given in the problem, that is small q is greater than 0, that non-negative charge small q on plate beta, why was that given at all? It is because, now let us assume, I'll show you why that was given. Listen very carefully. If we now try to add this all electric fields, all these vector equations, and do we know whether q1 or q2 is negative or positive, either of them? We do not know about the nature of the charge. We only know there are some arbitrary charges q1, q2 as they have got redistributed, and it is very non-intuitive that they are of a particular type or are they unlike at all. All we know is that there are some arbitrary charges q1, q2, and we are to find them. First, let us assume that q1 and q2 are positive, right? As you will see, we'll get surprising results. So we add the electric fields assuming q1 and q2 are positive. So the total electric field at O must be 0. So that is basically, this is what we get, right? If we compute that expression. This must give us 0, right? Now in this expression, see what happens. See what happens. Basically, if this small charges q1, q2 are positive, what are we getting if we solve this equation? We are getting q as q1 plus q2. Tell me, is this possible? This is not possible, right? Why are we getting this? Because we have assumed that both q1 and q2 are like charges. Both of them are negative or both of them are positive. This is why we are getting this expression. The math tells us that. But don't you think something is wrong? Yes. According to law of conservation of charge, as you might recall from our equation 1 we got, that was something different. We got that q plus small q is q1 plus q2 plus q2, which means that q might have to be 0 for this thing to be valid, and hence, as it is given in the problem that small q is greater than 0, this expression was given to signify that you cannot afford to take small q as 0. It is given, it is non-zero, it is something which is positive, and hence this expression is totally invalid. This is how you rule out this possibility. You are getting a possibility when you assume that q1 and q2 both are positive. This is what you get when you evaluate this thing. right? We do not know the nature of q1 and q2. We have assumed both of them to be positive as one of the possibilities. We'll consider another possibility where they are unlike charges, but when we are considering they are like charges, we are getting this condition which is mentioned in red, and it violates the law of conservation of charge, which is saying something else. And at this point somebody can raise a question that, no, wait, small q can be 0, right? No, it cannot be, because it is mentioned in the question that small q is greater than 0, so obviously this thing is wrong, and we discard this possibility in the first place. So now let us consider the other possibility, that is small q is obviously non-negative, but the other possibility is this was plate alpha, plate beta, plate gamma. Anyway, the other possibility is that, what was the other possibility? It was that the total electric field, we would get something like this. Let us assume that this was the beta, this was alpha, this was gamma. So charge on beta was q1 and charge on this is after the collision takes place. So basically charge which is redistributed among beta and gamma are like this, and we assume they are unlike charges, which means let us assume before solving that q1 is positive, q2 is negative. What will we get if we apply the thing that the electric field at this point will be 0 when this plate comes to and collides with plate beta? When plate gamma comes, accelerates and collides with plate beta, there will be a point at the junction of their collision which will have 0 electric field. So we will get something like this. If we assume q2 is negative, q1 is positive, right? And if we solve this, what are we getting? We are getting a condition which will help us to find out the charges. This is one important equation, and this certainly does not violate the law of conservation of charge. So we can use equation 1, which is the law of conservation of charge, and equation 2 to get the new redistributed charges. So let us find out the redistributed charges q1 and q2 by using equations 1 and 2. So equation 1 gives us that capital Q plus small q is q1 plus q2, the law of conservation of charge, and q is non-negative, and it is in fact greater than 0 as well, strictly non-negative. And we also get that capital Q is q1 minus q2 from equation 2, right? So if you just add these equations, you will get that this is what you get. So the charge q1, that is the charge on the plate beta, is so much, and let me bring it here. Yeah, this is one expression, and the other expression, which is the charge on plate gamma, q2, is this much. These are the magnitudes, and as you know, if we assign signs to them, then q1 is positive, q2 is negative in our computation. You can just swap this thing, you can swap the signs, but what matters most is the thing that q1 and q2 are unlike charges. If you take them to be like charges, well, perhaps you will violate the law of conservation of charge. As I have shown you that in the problem it is given that this charge is non-negative, and it is in fact greater than 0. So this is not 0 in the first place, it is strictly greater than 0, and hence charges q1 and q2 are unlike. So you will get the same result if you take q1 to be negative and q2 to be positive, but they are unlike charges. This is the importance, the physics behind taking or giving this condition that this is greater than 0. This was the importance or the physics behind giving. And now we proceed to the third part, the most important part of computing the velocity of plate gamma after it collides with plate beta, and then it is perhaps retracing its path, as you would expect it to be a possibility of collisions, right? Elastic collisions. And as I'll show you in the next video, perhaps that won't be a software based video, so there I need some pen and paper, because that's the most important, hard and challenging part. Didn't I say hard? Well, it is more of challenging and interesting, as you will see that when I solve it, it is quite easy to understand, and I'll solve it in two different ways. The third part is what makes this problem so much nice and interesting and challenging and intrigue. And as you shall see that we will use two different approaches, one of the work energy theorem and the other of basic kinematics to solve that problem. And there will be some analogous character between those two approaches, and you will be surprised that this type of a beautiful hard problem can be solved with such simplicity. The process I have discovered is that of by using kinematics, and the process mentioned in the book uses work energy theorem, but both of them appear to be in widely different spectrums of procedures, but they are at an analogous level, like they are almost having some kind of analogous character, which I'll discuss. But this is the end of the second part of this problem, right?